In this assignment, we're going to do some notes and practice problems about current, voltage, and resistance in DC series circuits. So let's start with current and voltage and resistance. Current is shown by the capital letter I if we don't know what the measurement is. If we want to show the variable, capital letter I is how we symbolize it in an equation, kind of like how we can use a capital F for force, a lowercase m for mass, and a lowercase a for acceleration. Current is measured in units of amperes, which is the name of a dead guy who did a lot with electricity, his last name. This is a lot of times shortened to amps, AMPS, or if you want it even shorter, the symbol for the unit is a capital A. If you have a higher current, in other words, a higher number of amps, a bigger number of amps, like 10A instead of 1A, that indicates a faster flow of charge. And generally, you're supplying more power to whatever's in your circuit. A lower current, a lower number of amps, means you're going to have a slower flow of charge. Voltage is like your driving force in the circuit. It's what causes your electrons to move in that loop. And it's measured in volts, named after the last name Volta, another dead guy, symbolized with a capital V. A higher voltage means you are pushing on the electrons harder to get them to move through the circuit faster, which means you have a higher amount of amps of current. So a higher voltage means a higher number of amps. So I'm going to say higher A, which also means a faster current. A lower voltage means you have a lesser driving force, so your electrons aren't going to be moving as quickly. You're going to have a lower number of amps, so I'm going to say lower A, and therefore a slower current. Resistance is measured in units of ohms. Yet again, the last name of a dead guy. And you'd think since amps was A, volts was V, ohms should be O, but if we write something like 10 ohms, like this, it kind of just looks like the number 100. So in order to show things correctly and not get this symbol for ohms confused with a number 0, we use the Greek letter omega that looks something like this. It's kind of like an O with feet, sort of. Resistance is about kind of the subatomic friction, essentially, of your particles moving through a wire or a conductive material. So the electrons bumping against each other and against protons and things like that as they're on the move. So a higher resistance means it's harder for electrons to flow through your circuit, which means we should have a slower current and therefore a lower number of amps. So the higher the resistance is, the lower the number of amps. So I'm going to say lower A, and therefore a slower current. Whereas if we have lower resistance in the circuit, we're not keeping the electrons from moving so quickly. We aren't kind of giving them as hard of a time. We would end up with a higher number of amps, higher A, because there is a faster current. So voltage and resistance kind of act against each other to result in the current. How fast the electrons move through your wire essentially comes down to how hard the voltage is pushing and how much the resistance slows them down. So the current is like the result of your voltage and your resistance competing against each other. Now, because they are related in this way, your current should be equal to some relationship between the voltage and the resistance, which means we can make a relationship between any of these three as long as we know how to rearrange things. So let's scroll on down here. Like so. All right, so we're going to write three different versions of an equation that have to do with relating voltage and resistance and current. We're going to start with voltage. Voltage V is going to be equal to, well, this handy-dandy triangle over here is kind of a shortcut for making the equation we need. Okay? If I sort of cover up and ignore voltage and the symbols next to it, what I have left is I times R. I being your current multiplied by R, which is our resistance, something like that. Now, this isn't the most useful equation because the way it's set up, we're solving for voltage. But voltage is actually pretty easy to find. Even if you don't have something like a voltmeter, which can measure your voltage there, if you have a pair of fresh batteries, it says the voltage on the label, on the outside of the battery. So as long as that battery hasn't been used up for years and years, the voltage of your battery's got to be pretty close to what's on the label. Now, it is going to be different. Maybe it's going to be 1.6 volts instead of 1.5 in reality. Or maybe it's been used for a while and it's more like 1.48 volts by now. But it's going to be close enough to approximate with some calculations if you can see what's on the label and the battery is relatively new. So, yes, it does help to be able to calculate voltage, but you can also measure it with a voltmeter. So we have kind of two ways we can go about it. We can trust the label on the batteries, or we can measure it with a device that's specifically made to find voltage. So we don't often need the equation set up like this. But we can rearrange it, either with algebra or the shortcut on this triangle. If I wanted to rearrange it algebraically, V equals I times R, where this dot here means the same thing as this multiplication sign. I'm just changing it up a little bit. If I wanted to get an equation that had I equals something, what I would need to do is get rid of whatever is next to this I for current. So if I want I equals, I got to get rid of this R. To get rid of something in algebra, you've got to do the opposite of whatever's happening to it. So if I'm multiplying by R, I do the opposite and I divide it. I'm going to divide by R right here. Now, to be fair, this equal sign says whatever I do to the right side, I also have to do to the left. So I'm also going to divide by resistance on the right side here, or on the left side, sorry. So on the right side, R divided by R is going to cancel out. It essentially becomes 1, and 1 multiplied by anything is the same thing that you had before. If you have 4 divided by 4, that's 1, and then it kind of goes away. And whatever it multiplies to stays the same. 10 divided by 10 cancels out, 2 divided by 2 cancels out, a million divided by a million cancels out, and the same thing goes for variables in units, like these guys. So these will cancel. All I will have left here is that current I is equal to voltage divided by resistance. And if I use the shortcut method here and I cover up current and the symbols next to it, that's exactly what I get. Voltage divided by resistance. Okay, this is just the shortcut for the algebra. So let's write that in here. I for current is equal to our voltage V divided by our resistance R. This one's a little bit more useful, but we do still have a way to measure current. There's a thing called an ammeter that can measure current, measures amps. So you can hook up an ammeter into a circuit to tell you the number of amps that you have flowing through it, the flow of the charge, how fast it's moving. So even though we don't have something packaged on the wires that tells us the current, because it's going to depend on what else is in the circuit, we can still measure it pretty easily, as long as you have the equipment. Okay? So this can come in handy, but it's not the most useful equation. What I would say is the most useful equation has got to be this last one, where resistance equals something. Because you can't often go and find a resistometer, something that is specifically made to measure resistance. You can find voltmeters, you can find ammeters, but resistance is kind of tricky. So we calculate it in a lot of cases. Resistance is going to be equal to, if we take the shortcut, cover this up, voltage divided by current. So if I take the voltage that I know, maybe from a voltmeter or from the labels on batteries, and I divide it by the current that I can maybe measure from an ammeter, then I can find what the resistance in the circuit should be. So these are 3 equations that we can use, and all of them come in handy in different situations. I tend to find that this equation with resistance equaling voltage divided by current being the most useful, but even then, you can find equipment that can measure resistance. A multimeter is basically a combination of your voltmeter, your ammeter, and something to measure your resistance. Although most of how a multimeter works kind of comes down to analogs and calculations of what we know about these three things. So it's all kind of related to the math in one way or another. So as long as you have two of these things known, current and resistance, or voltage and resistance, or voltage and current, you can find that third missing thing. Something else I want to mention here too. Sometimes you'll see these equations written like this. So if I clean this up a little bit, V divided by R equals I. Sometimes you'll see it written like that, where there's a bar. Okay, that fraction bar is the same thing as dividing with a division sign. And the order of whether it's on the left and what is on the right doesn't change anything either. So whether you have something written like this with a division sign or whether something is on the left or the right doesn't really matter. You can plug it in either case. So let's do an example. Let's look at number 4. If a circuit has one 9-volt battery, 9 volts, and one 10-ohm resistor, 10 ohms, calculate the current, I, in terms of amps. Okay, so we have two of those missing things. We need the third. So I want to use this equation right here, that current is equal to the voltage divided by the resistance. So I'm going to write it out all in line. So I is equal to my voltage V divided by the resistance R. Okay, kind of like I have my equation written up here. So I equals, I can plug in my voltage of 9 volts, 9 volts divided by my resistance of 10 ohms. So I'm going to write in 10 ohms in place of my resistance. And that's going to be equal to whatever this comes out to be on a calculator. So if you type this in, 9 divided by 10 should give you around 0.9. And the symbol for current, the unit, is amps, capital A. And that's my answer. Well, that was kind of a bad circle. Let's try that again. That's a little bit better. So 0.9 amps would be the current in this circuit. And what's cool is you can actually go make this circuit in the simulator. In the circuit simulation, you can build a circuit that has one 9-volt battery and one 10-ohm resistor, and then use the ammeter on the circuit to see what the current is, and it comes out to be 0.9 amps, which is pretty great. So it's almost kind of like a little answer checker for you. Now, again, this is idealized. So in real life, these numbers are not going to be nice and perfect, but this is how the math works. And the math works even if your numbers don't come out to nice, clean 9s and 10s and 0.9s and things like that. Number 5 and number 6 work by the same kind of system where whatever we're trying to find, like resistance R, we need to use an equation where we're solving for that missing thing, like R, and then plug in the values that we do have, like a voltage of 3 volts and a current of 0.15 amps to solve for that missing thing, like resistance in ohms. Number 6, we're using 20 ohms of resistance, and we have a current of 0.2 amps. So we want to try and figure out what the voltage is driving the electrons in that circuit. Okay, so if you can find an equation that's V equals, plug those numbers in, and then the calculator does the rest of the work for you. Now, what if you're using a circuit that is a little bit more complicated, which isn't just one battery, one resistive element? What if you have multiple things? You have multiple batteries, you have multiple resistors, multiple light bulbs, things like that. You've probably noticed that whenever you plug batteries into something, it's almost never just one battery. It's like 2 batteries or 4 batteries or sometimes 6 batteries. So how do we deal with a situation like that? Now, as long as your circuit is in series, which means basically everything is all in one loop, all the things providing voltage, that driving force, in your circuit add together. When you have one battery that's pushing and another battery that's pushing in the same direction, you just add up their pushes. So the total voltage in a circuit is just equal to all the individual voltages added together. So maybe you have V total equal to V1, which would be like the voltage of one of your batteries, plus V2, which would be the voltage of a second battery, if that was in the line, in the loop of the circuit in series. If you have a third battery, we would add V3. And you could do this for as many batteries as you have. If it's just the one, then your total voltage is the voltage of that one battery. If there are two, then you add up those two batteries to get the total voltage. If there's three, you add up all three, and so on and so on. If there's 10 batteries, you add up all 10, and that is the total voltage in your circuit, driving the electrons around and around and around through that loop. And we do the same thing for the total resistance. As long as everything is in series, in the same loop, your resistance totaled up, we call R total, in your circuit, is going to be equal to the resistance of one resistor plus the resistance of a second. And if you have three, you could add up all three, and you do this for as many resistors as you do. A lot of times we simplify light bulbs to basically be resistors with a purpose. And same goes for a lot of other electrical equipment that we might be trying to power. Now, what's nice is since the current is the result of your voltage and your resistance kind of fighting against each other, the current is going to be the same all the way through the series circuit. It's going to be equal all the way through. So I'm going to say the current is the same all the way through the series circuit. So it's not like we have like fast parts and slow parts where the electrons are like really moving quickly at the beginning and then they like slow down as they go through the resistor. They're all moving at the same rate through the circuit, which doesn't always seem to kind of line up with your intuitive idea of how things should work. If we're talking about voltage as the thing like driving the electrons and the resistance slowing them down. But the way I always think of it is that since everything is in a loop, whatever comes back to your battery and comes out of your battery has to be the thing that eventually goes back in and comes back out again. So if you have something that's going fast and then it slows down, you're going to end up with kind of like a blockage. It's like a traffic jam, essentially, of electrons, which is not going to work out real well. Your electrons have to continue flowing, which means they're going to be going at the same rate all the way through your circuit. So as long as we've got a track on what the total voltage is and what the total resistance is, the current is going to be the same. Okay? We don't really need to have a total current or anything like that where it adds up for a series circuit. So I'm going to modify these equations a little bit up here to include the fact that these can be totals of multiple things, giving you voltage or resistance. So I'm going to say this is V total, V total, V total, and then resistance total, R total, R total. So again, if you only have one thing to give you voltage or resistance, the total is just that one thing. The only thing this equation has done is allowed for extra stuff that might be in your circuit. So let's look at some examples using total voltage and total resistance. Let's look at number 8. Okay, we're going to do 8b. What is the total resistance in a circuit that has 4 10-ohm resistors? So in other words, in the circuit loop somewhere, we have a resistor and a resistor and a resistor and a resistor. All 4 of these resistors have 10 ohms of resistance that they provide for this circuit. The total resistance then is just going to be all of that resistance added up. So I'm going to say R total is equal to the 10 ohms from one resistor plus 10 ohms from a second resistor plus 10 ohms from a third resistor plus 10 ohms from a fourth resistor. Or if you have a whole bunch of them and you don't want to have to add them all up separately, you could say if all 4 of these are 10 ohms, I can kind of skip having to add them all up separately and say 4 times 10 ohms should get me the same result, which should be equal to 40 ohms of resistance total in the circuit. Circle that. Okay, I'm going to leave 8A for you to do, where you have two 9-volt batteries giving you your total voltage. I think you can figure that part out. Just add them up. Let's look at a couple more examples here. So a circuit in series has a total resistance of 15 ohms and a current of 0.6 amps. The first thing we're going to do is calculate the total voltage. Okay, well, usually we could calculate the total voltage just by adding up the voltage of all the individual things in the circuit that provide the push for your electrons. But this doesn't tell us that. It doesn't tell us the voltage on the number of batteries we have in the circuit and how many batteries we have. In fact, it looks like we start getting some information about that in B, where we still don't know the voltage on a single battery, but we do know there's 6 of them. So we have to kind of come about this another way. I can calculate the total voltage in the circuit based on the current and the resistance in the circuit, as long as I can find an equation that links the two. So if I go back up here and find an equation that says V equals, hey, like this one, V total equals I times R, specifically R total. So I'm going to come back down here and rewrite that equation. V for voltage is going to be equal to my current I multiplied by the resistance R. If I plug some of that in, V for voltage, and I'm going to say V total, be specific, is going to be equal to, let me scooch this over a little bit. Give this some room. Equals V total. My L got messed up there. Nice. It's going to be equal to our current running through the circuit, I, multiplied by our total resistance, R. Oops. Except I have these values, so I should just plug them in. Oops. Scooch this over. Oh no, I'm taking my equal sign with me. Okay, I think now I can squeeze this R total in here. Here we go. So our V total is going to be equal to our current, which we said is 0.6 amps. 0.6 A multiplied by the resistance total in our circuit, which is 15 ohms. So all I have to do is multiply those in a calculator. Okay, if I take 0.6 multiplied by 15, I get 9 volts total. Now, what's kind of interesting is that a 9-volt battery is actually just a bunch of smaller batteries added together in the same package. So let's say that we have 6 batteries in series, in line with each other. We can figure out the voltage of each battery as long as they are all equal to each other. Okay? In other words, I have something like this. I've got a battery with some voltage. Copy and paste. Oh, that's right there. We got a battery, copy and paste, battery, copy and paste, battery, copy and paste, and a battery. So I got 6 batteries all lined up here. And in total, their voltage is 9 volts. They are providing 9 volts to this circuit by having all 6 of them added together. So if I want to figure out the voltage on just one of these, all I have to do is take that 9 volts total, divide it by, how many batteries I have. 6 batteries. If I split that 9 volts equally into 6 different batteries, I'm going to end up with 9 divided by 6, which if I plug that into a calculator gives me 1.5 volts. That's my voltage per battery on each battery. And with 6 of those add up to 9 volts. Okay. So I mentioned that a 9-volt battery is actually a package of smaller batteries put together. There are 6 little batteries inside a 9-volt battery. And if you ever look up online what a 9-volt battery looks like inside, or you are safe with it and crack one open yourself, you can see those little tiny cylindrical batteries that are kind of like smaller versions of like a AA or a AAA battery. AA's, AAA's, C batteries, D batteries are all 1.5 volts based on the chemical reaction that drives the electrons through them. If you're dealing with a D battery versus a AAA battery, the only difference is that the D battery is bigger because it holds more reactants to make your reaction happen. So you can essentially have that battery last longer. So with 6 1.5 volt batteries slapped together, you have one single battery that's at a higher voltage, but that uses the same chemical reaction as a battery you're already manufacturing, as AAAs and D batteries and C batteries and so on. So if you need a higher voltage regularly and you don't want to have to get a new chemical reaction to provide that voltage and manufacture it separately, you can just get the old chemical reaction and put some cells of those batteries together and package them into a new battery that has a higher voltage because we tied them all together. We put them in series with each other. Okay? And that's all really a 9-volt battery is. Okay? For other situations where you might not have specifically some voltage needed as commonly, like maybe you have 4.5 volts are necessary, or maybe 6 volts are necessary, or maybe just 3 volts are necessary, then you can also just have multiple AA's or AAA's or D batteries in line with each other. That's where you have like sets of 2 or 4 or 6 AA's or AAA's to get a higher voltage. Instead of making a whole new battery, if it's not as commonly needed, you just put a couple together in line with each other in series to total up to the voltages that you need to power that device. The same idea applies to our resistors in series here, where again we know the total resistance is 15 ohms. We want to know what the resistance is going to be on each resistor, where each one is going to have an equal resistance. So if this is a resistor, and this is a resistor, and this is a resistor, and all together, that's 15 ohms. We have to figure out what it is for just one of these. Okay? And the math is very similar to part B. Okay? So we can use this math with some actual circuits, and you can also check it in the digital circuits to make sure that everything comes out correct, to figure out things that might not be so easy to measure. We can always calculate the missing things instead.